So this is the very nice theorem that you should always use whenever you're trying to find the eigenvalues of a square matrix. It says trace of A is always equal to the sum of the eigenvalues. In this video, we'll demonstrate with a 2x2 matrix. Here we go. First, finding a trace is super easy. It's just you go to a diagonal and you add up the entries. So it's just A plus D. Let's focus on the eigenvalues. In order to get the eigenvalues, we need a determinant of A minus lambda times the identity matrix is equal to 0. So we go to the diagonals and then just subtract lambda from it. So we have A minus lambda, and then this B and C stay the same. And then here, D minus lambda. And make that equal 0. And then work this out. So this times this. Minus this times that. That's equal to 0. Expand this. We have AD minus A lambda minus D lambda plus lambda squared minus BC. Now, this right here is a quadratic equation in terms of lambda. I'm going to put this down first. And then right here, notice that I have negative A minus D. I'm just going to write it as minus parentheses A plus D, and then times lambda, and then these are the constant terms. So I say plus AD minus BC, that's equal to 0. Here we have a quadratic equation. We can always solve it if you allow complex numbers. So of course you can just go ahead and use that. I'm just going to call the roots lambda 1, lambda 2 be the roots to this equation, which lambda 1, lambda 2 will be the eigenvalue of this. So just think about it. If you have lambda 1, lambda 2 be the roots of this equation, we can write this in the factorial form. The coefficient here is 1, so this means we can factor it and we get lambda minus lambda 1 times lambda minus lambda 2. And you can also use the Vieta theorem. I'm just trying to demonstrate how the Vieta theorem really is, that's all. Right, we have a 1, right? Okay, and if you expand this real quick, you can see that lambda squared, and then you get negative lambda 1 lambda, and then let's do this times that, which is minus lambda 2 lambda, and then lastly plus lambda 1 lambda 2, and that is equal to 0. And notice this right here, we can factor out the lambda and then put that in this form. So I'm going to factor out the negative, and then it will be lambda 1 plus lambda 2. So here we will have lambda 1 plus lambda 2. And now if you look at this equation, that equation, this and that match, this and that match, this and that match. So we must have A plus D being equal to lambda 1 plus lambda 2. And in fact, you can also see that lambda 1 times lambda 2 is equal to the original determinant, which is pretty cool, but we don't need to worry about that. So as you can see, combining these two things, we get A plus D equals lambda 1 plus lambda 2. And this is precisely our trace. And this right here is precisely the sum of the eigenvalues of our matrix A. So we're done. And the beauty of this is that it also works for any other dimension, n by n matrix. That's it.